Okay, and we'll get into form tolerance. We get into flatness right here. All right. Sorry, 201 has a lot of material, yeah, and just be patient. But once you go through it, it's the same thing. Yeah, we see this again and again in your profession, of course. And here, flatness, yeah. So that's just showing you a little cartoon for you to de-stress you. Okay, and then we get into our usual flatness tolerance and zone. Yeah, we will see them, each one of them. So I'm not gonna waste my time on reading that for you. You can skim it. Yeah. Of course, flatness is you can see it, but when we got to write it, yes, write it or show it on a screen or paper, then you have an issue. So then we always have to use a theoretical plane for us to be able to describe the flatness on the paper or in the program. Of course, I'll show you in each diagram, because we can only deal with 2D and 3D anyway, so it's a little bit difficult. Of course, when you look at it outside, you can be able to feel the flatness of an object with your hand. So, from away, we're gonna say oh, that's the high point of a control surface, in contact with a surface plate or gauge, so gauge is a measurement device that you will measure the flatness of a surface, So we're dealing with the high points of that surface, which is in contact with this. Okay, that's what it's talking about. So from your theoretical plane, we're going to have a second plane, and that is going to be offset in parallel, by a distance. Since you have a parallelism, you always have a distance, away from what you're measuring against to your total tolerance, value. So all elements of your control surface got to lie between the two parallel planes. So here we go, your object and then your gauge. Of course, your primary plane is right here, your second plane is right there, and here this little between the primary and the second plane is where you're gonna examine your flatness, and that's your tolerance zone. And when we say the high points, this one right there. So all of the elements, your control surface got a line between the two planes, so we can be able to determine how flat that is. So that's your surface plane. So flatness, how do we measure? You can verify that or inspect the flatness by using a dial indicator. We're going to extend that device right through a hole. Here is your hole in a surface plate. So the dial indicator is made stationary. Right there, and the part, your part is moved around on the surface plate, to ensure that all elements of that control surface are checked. Meaning like we're checking that surface, all of it. So this little thing is going to scan, of course, so from here all the way to there, because you are moved around, on this surface plate to check the flatness of it. Alright, so the flatness tolerance is allowed to float within the larger size, right, tolerance. So here you can see your dial, indicator right there, and here you can see the flatness sign symbol here, and then you have 0.2 for the flatness tolerance, or for this feature, which is your surface, Of course, your size limit is given here for you, from here to here, 16.0, 16.0, and 15.4 right there. So that's 0.6 millimeter allowed, with your general rule, because we're dealing with a surface right here. So as long as the flatness doesn't violate this size or limit, you can be able to orient. It can be oriented in any direction, as long as it stays within this size limit, right, which is 0.6. So your surface, all the surface element right there, got to be within that tolerance zone. Here, the tolerance zone, which is given in your control frame, is written here as 0.2, your geometric tolerance, it's got to be within that, all of your surface elements. And like I said, you have to go over and over again, so that way you are familiar, with what's going on by looking at it again and again. If you are skipping the lecture, I don't know, these are things that you can't understand just by reading it, even we will have to look at it again and again, the same thing. So tolerance of form outside, and this is what we're talking about. You have your surface plate, this guy right here, and then the height stand, and then your dial indicator. Here we're using the inspection verification setup, and we have a rotation. This is a rotating. You can see it very clearly. Surface plate, and then your height stand, and then your digital indicator is taking a measure for that. Flatness, it can be applied to the planar surface. Is applied in a view, where your control surface is going to appear like a single line. We have already seen that in our two-dimensional drawing in the previous slides. So flat surfaces references its own true geometric counterpart, so we don't have to deal with the datum references. That's what it's saying. So in your control frame, there is no datum attached to it, so we don't use the datum references. In conjunction, when you deal with your flatness control, so flatness always apply regardless of feature size. Again, your RFS. So you don't have to use your modifier, your MMC or LMC, because it always applies regardless of your feature size. Your flatness control never override your rule number 1, because your flatness got to be between that upper and lower size limits, and it's got to be smaller than the size tolerance, and it's going to give you the lava flatness error, and it's got to be within the size tolerance. All right. The very first fundamental rule is your default flatness. You control with this first rule. So your coordinates, again, your coordinate tolerances combined with the first rule apply to the feature size. Your feature size is nothing but the distance between the two parallel surfaces. And it's going to give you your automatic flatness control for both surfaces. They're attached anyway, so I mean like attached to each other, or I shouldn't say attached, in contact with each other. So if you have like an MMC, then both surfaces got to be perfectly flat. If you have a departure from MMC happen, you will have variation, and that variation equal in the amount to that departure is allowed. So form variation limits are equal to the difference between the upper and also the lower size tolerance. And you're going to apply equally for both surfaces. So because of the rule 1, right, your size limits, you cannot violate it, because your rule 1 depends on that feature size limits. So let's take a look at the application. So here you have your control frame, which is attached to, here. So that's your extension line dimension right there. So what's weird about this, see how the control frame is attached to the extension line. And that's what is written here, Sometimes the control frame is attached to your leader line, So it's a different ways of writing, but doesn't matter how you write it, but it's always have to be associated with the correct view, appropriateness of your view. And what kind of view? The view that is going to show your surface, being controlled by this, control frame is appear as a single line, so which is this one, Of course, we call that the edge view. All right, let's go in the next one. So the top surface right here, it's got to be flat, of course, within this tolerance zone, and we usually show it with a little two parallel lines, and the parallel lines come from your parallel planes, which is in this case 0.2 millimeter apart from each other. So the size dimension is going to allow for this, size limits right there, So that's a 0.6 millimeter tolerance between the two surfaces. So that's your size dimension allowance. Now we're gonna start drawing that bigger, here. So you can see your 14.0 and then 14.6, your least, your max. In between, you have your surface. See that, So that part is, of course, within the tolerance range. But the flatness tolerance, also got to be within the tolerance, within the size tolerance. Flatness tolerance, the size tolerance. So let's take a look at it. Now we're going to bring in our flatness tolerance with a little two lines right there. See, little tiny lines of blue line. So that's a 0.2, tolerance zone right in there. So your surface is outside of that zone, in this case. All right, then we're going to bring that tolerance zone for the flatness, up a little bit, yes. So the elements is going to will not fit within the tolerance zone, but we just take it like the top is flat. There is no relationship to the bottom, other than the size dimension right here, from here to here, 0.6. You take it a little bit up right there, so that way, see right here, you can see, the very top, right, portion of your surface is within this 0.2 tolerance zone. So even though like that, we still take it like, that is, that's flat. Okay. Then we're going to put a little gauge. So when you put it, it's going to elevate, about this much. So see now how the surface is now within the 0.2 tolerance zone, see, because we tilt it like that. And we carefully look at it, of course, all the elements of your surface are now within this tolerance zone, So by applying the gauge, at the bottom of this part, we can get all the surface element within the tolerance zone and also in the side zone, So that's a tolerance for the size and then the form, This is just showing you how we apply the flatness, in real situation. So here another shape, flatness 0.4 tolerance. Then we also have a size tolerance 6 all the way to 7.2 mmc, your LMC. You subtract it, you're going to get the first zone, second zone is 0.4. We're going to put it all the way up, beyond this 7.2 mmc. See how it go up. So in that case, you have to compromise some of the form tolerance zone, Why? Because you cannot violate the size limit. So we have to bring that, between this LMC and MMC. Here's a very big view, exaggerated view or blown up view. You have your max, and you have your 0.4 tolerance zone, which is a blue one. Your max is 1.2, So at MMC, the surface got to be perfectly flat, But all surface elements got to be within the size, tolerance zone. Of course, here we don't have a yellow, we have just a regular because this is adjusted to fit your printer, when you have to print it, so it's easier for your ink intake. So 0.4 is completely compromised because it's over this MMC limit right there, Okay, another way that we apply the flatness is just like your straightness, we can apply per unit basis. So here we're gonna go by using this composite feature control frame where you can be able to see the length unit right there. So here it's just saying we're going to go 0.2 per, every 25 by 25 millimeter area surface, So you have like 0.2 tolerance allowance for this area, yeah? Accompanying with your 0.6, of course, your maximum distance, yeah, between your two parallel planes for that surface control for your flatness application. So let's take a look at it. So now we draw. Here is your surface, yeah, and here is our first zone, right? And leader line is showing you the surface right here. So this one, yeah, 25 times 25 is telling you about your area, yes? So any 25 by 25 on here, on this part is okay. And tolerance is 0.2 for that condition. Again, your geometric tolerance for flatness, you cannot override your size, yeah, limit. You gotta be in it. So that's your first rule. Geometric flatness control is gonna take effect only as a part, yeah, varies from your max, yeah, by more than the allowed flatness tolerance. Already show you the diagram. And your single surface flatness tolerance, you should typically be a refinement, yeah, of your size tolerance. This is just showing you how your flatness tolerance is related to your size, yeah, your size tolerance. You have two different tolerance, by the way. You can see the zone, yeah. We've been looking at it again and again, the same two things. And your VC is your virtual condition of a part. It's not affected when it is controlled with a geometric tolerance or geometric tolerance for flatness. Okay, review. So these are all the important points that you at least need to hit. So the very first one is a geometric tolerance for flatness. Yeah, cannot override the size limit. Again and again, it's got to be in it. Yeah, you cannot violate it. So that's your first rule. Geometric flatness control is going to take effect only as a part varies from your MMC by more than the allowed flatness tolerance. Yeah, second one, I already talked about this, yeah, in the previous slide. And of course, your single surface flatness tolerance should typically be a refinement of your size tolerance. They are always related anyway. The virtual condition of a part is not affected when it is controlled with a geometric tolerance for flatness. Okay. All right. Now here is in a box that you gotta pay attention. So based on your design, yeah, sometimes your flatness tolerance is going to be larger than your size tolerance. Okay, so what kind of case is that? Is your gasket, you know, may not need to be controlled for flatness when you deal with these parts outside to the same extent, you know, that the thickness requirements got to be met. So for this type of situation, meaning like, you know, when that happens, yeah, in the real life situation, all you have to do is just put a note, yeah, put a note saying, oh, we don't need a perfect, yeah, form at MCC. So here is a note to clarify the exceptions. A perfect form at MCC not required. You can note it down, yeah. So that way, this type of example is allowed, yeah. Okay. The same thing, yeah. We have an indirect control. So if you have like a geometry tolerances, they're specified without a zone, right? So if you don't have anything identified in your control frame for your tolerance, then you just go with a two parallel line for the tolerance zone. Because all surface element, right? Because we are measuring the flatness of it to make sure that flatness stay within the tolerance. You've got to make sure that they stay between the two planes, the primary and the secondary planes in between the two surfaces. So that's the only way to control the flatness. So now we're going to bring in other geometry tolerances: angularity, parallelism, perpendicularity, profile, total, and your Reynolds. Yeah. So when they come in indirectly, control the flatness. Yeah. Because in the real life, you always have these geometry controls on your different features on the same part or the product. Yeah. So therefore, so other geometric tolerances will always indirectly control your, in this case, is your flatness, yeah, flatness control. So that's all they say, yeah, there's an indirect influence from other geometric tolerances. Okay. Okay, we'll go into application, yeah, your flow chart. So we start with same as before, yeah. Apply to the planar feature for flatness, yes or no. Yes, and we're gonna look at the view. Yeah, control surface shown on the edge or not your single line. If yes, we're gonna look at the modifier, if they use or not. No, we're gonna look at the datum. We're gonna look at the other, yeah, GDT controls if there's an indirect. Yes, we're gonna look at the datum, yeah, reference in the feature control frame. No, and it's acceptable. Yeah. If you don't have your planar surface, unacceptable. If you don't have the appropriate view, unacceptable. If you have the modifier in the feature control frame, unacceptable. If you don't have the other, yeah, GDT controls indirect influence, then yep, it's definitely unacceptable. If you have a datum reference in your feature control frame, yes, that is unacceptable. Yeah, so this is your flow chart to check the guidelines, of course, for your flatness feature, yeah, geometric tolerance check right here. All right, then we'll get into a little mini quiz from your textbook, which is problem number 51. Again, I'm not going to read this for you. This is your homework and you have to do it. And here is your answer. Don't just copy the answer, by the way. Yeah, you have to struggle to do it by yourself. So again, they're writing about the same thing: modifiers, yeah, flatness control, and then your feature, yeah, feature of size. Again, the same thing. All right. All right. Then we'll get into another one, which is your circularity and your form tolerance. Yay! All right, so this is your circularity. All right, here is your definitions. Of course, I'm not going to ask you all the definitions. So if you can recognize it, you're okay. And of course, we will go over each one of them as we go into our lecture. All right, here's a little picture. You can be able to see your gauge, yeah. Of course, we use it in manufacturing part production, and how we measure the circularity in there, yes. Okay, so circularity is just a surface feature, another form control, yeah. Circularity is applied to an external feature, yeah. Since you're dealing with a circularity, you're dealing with a diameter, yeah, either pin or shaft, yeah, like that. An outer boundary, of course, you know, larger tolerance. Usually your circumference, yeah, of your circle. Usually we take the high points so that you will include everything on that, yeah, surface. So anyways, talking about, you know, what the circularity is, and let me break this up for you so it's easier for you to read. Okay. Of course, when you go into the inner boundary, from the upper boundary, we got the limit, yeah, upper limit and the lower limit. And we call that the size tolerance. Yeah, we see this again and again, so you shouldn't be unhappy about it. Yeah, the same thing: geometry tolerance, size tolerance, geometric tolerance. Okay, and we go each form tolerance: straightness, flatness, and now we're on circularity. Your rule one, the same thing: the actual feature at any point of the measurement. Okay, got to be within the size, again within the size limit. So that's your rule one. Yeah, the same rule for all different forms. All right, then let's get into then okay, the next one is a control. Yeah, so circularity control is going to be applied to the entire feature. Yeah, like your whole inner boundary, of course, your circle. Yeah, usually established by the gauge contact of the high points. I thought I already talked about. Okay, and then the outer boundary is radially larger than your smaller size tolerance. Yeah, this is where you again your size tolerance that you can get. because we always make sure that your feature got to be within the limits of the size, yeah, perpendicular to the axis. So here we go. Your circularity, yes, little circle right there, 0.4, your geometric tolerance. So this is your tolerance, okay? And of course, it is in your control frame right there, yeah? Feature control frame, showing you this, okay, surface, circle surface, circumference right there. So your circularity tolerance, 0.4 millimeter radius distance, yeah, of that circle. So in order for us to see the zone, you've got to come up with the two, yeah, circles, so that you can see, because most of the stuff that we deal with, yeah, so far a flat surface, so we have two lines. Now you have two concentric circles to be able to see that zone, yeah. All right, so now see, we have two concentric circles right there, so that's our zone for this tolerance, okay? And of course, here is your center, here is your centers for your shaft. Your control, smaller circle, okay? These are just your circumference, by the way. Your high point is, of course, within that tolerance, yeah? High point of this surface, this circle surface. Of course, we start drawing, yeah? So you can see the part right there. And part surface, yeah, which is this guy, is within that tolerance zone. This is exaggerated view, by the way, yeah? So from outside, you can see only that. Of course, we go micro view, then you can be able to see the surface is like this. Yeah. So it's about like a 0.4 offset of your concentric circles right there to show this a 0.4 tolerance zone for you, yeah? And you gotta pay attention that it's okay because it's still inside of that tolerance zone, yeah? And it's cover all of the high points of that feature, yeah, diameter within the tolerance zone. Okay. So diametrical feature like your cylinder, your cone, your spheres, yeah, they are the features that your circularity can apply to. So when you deal with that, make sure you deal with this circular control, yeah, over these features. So circularity, you cannot modify it. You cannot be modified, yeah, to apply your MMC or LMC. It's going to go with your size tolerance again and apply a general rule one, yeah. And of course, it's got to be the perfect part because you're dealing with the rule one, yeah. When your part is at your MMC, circularity always applies regardless of, or your FS, regardless of feature size. And it's got to be contained within the boundary of that, again, size limit, yeah, the same thing. Okay, so rule one is your default controls for your circularity, very similar to everything that we have learned so far, straightness and flatness. So your circularity control, again, automatically apply, yeah, under your rule one. Your MMC, your perfect circular form is totally required, okay, at that condition. Your feature size is going to depart from MMC, and you're going to get every time something depart from MMC, you're getting the variation in that feature, yeah? So from true circular form at MMC, it's going to go down, yeah? However much you get smaller. So allow the variation from your perfect circularity is equal to the amount of the departure from the MMC, okay? So as you go towards LNC, your perfect, yeah, your perfect circularity reduces. Okay, so here is our example, and we have 0.8 millimeter, which is this difference, yeah, that's your size tolerance. So that's your tolerance, 0.8 millimeter is allowed, yeah, for the upper and lower limits of that tolerance diameter of this pin right there. So other than your size tolerance, we don't have a form control, yeah, we have only size tolerance given in this example. So here we go, and we're going to have a concentric circle showing 10.8 the upper and 10 the lower, yeah, and that's your 0.4, yeah, radial distance. Radial means coming out from this center point. So rule one is going to limit us, yeah, your boundary defined by this two concentric circles, yeah. Okay. All right, then we're gonna fill in our sheets. So we can see right here, yeah, size in the form right there. When you look at it, yeah, the size tolerance is when you look at it here, it's still in the zone. Yeah, here it's kind of like a protruding right at that outer suckle. So if your size tolerance is too large, yeah, your size is not, your part is not going to function. Sometimes it happens. So the foam tolerance got to be, yeah, got to be, yeah, not that large. Okay, so here is a reasonable 10.8 to 10 anyway. So about a 0.4 radial distance. So in this circumstance, yeah, where it's kind of like very close to the outer suckle, yeah, your size and form, they're allowed to vary within that limits of the size. Okay. What we have to pay attention in circularity. So whenever a tolerance diameter is called out, yeah, on a drawing and no geometric tolerance is specified, your control, we're gonna apply your rule 1, yeah, and we're gonna use a 2 concentric, yeah, suckle. The concentric suckles are equal to the upper lower, yeah, limits of your size for that diametrical feature. We have already seen that in our diagram. So the circularity on objects controlled by a combination of their dimensions, and rule 1 is restricted to 1/2 of their diametral size tolerance. So in other words, the radial difference between the upper limit and the lower limit of the diameter size is the maximum allowed variation from perfect circularity. Okay, so when these consequences going to threaten the integrity of that part function, because your part got to function. So if it doesn't, then alternate form control, yeah, you should use that, because we have to maintain the integrity of the part function when you manufacture, yeah. So therefore, even if we allow the variation, we can go, yeah, the maximum allowed variation cannot be violated. Okay. Alright, so now we have a feature control frame right there, yeah, showing you 0.4. Your size limits of 11.4 to 10.0, yeah. So you have the 2 concentric suckles over 0.4. Tolerance zone can float within the larger size tolerance, yeah. So here is your tolerance. This is your tolerance, yeah. Zone. This is your size, okay, tolerance. Very different things. So we have altogether 1, 2, 3, 4 right there. Yeah. So this one is a 0.4 radial distance. Yeah. Foam tolerance. Your size tolerance is this one. Yeah, which is your 1.4, because when you minus 11.4 and 10.4, so you're subtracting 10.0. 10.0 from 11.4. You're gonna get 1.4 millimeter size tolerance right in here. Yeah. So that's what you're seeing. And of course the lit up, so from here all the way to here. This guy is from here all the way to the little one right there. Okay, a little bit difficult for you to be able to see it. So anyway, so this is a radial distance, yeah, the tolerance is inside of the size tolerance. So that's what it wants to show you. And of course, and now we're going to put our part, yeah, material right in here, which is this guy. And so you can see this little red one is within within this 0.4 radial distance right in there, which is controlled by this feature control frame. Yeah, it said it's a feature control frame. This frame will control that circularity, which is your feature right there. Yeah, feature of this suckle. Okay, foam tolerance. Now we're gonna make it really big so you can be able to see that. Yeah, so your white is gonna be 10 to 11.4 millimeter diameter size limit, okay, from here all the way to here. And then of course from here to here is your 0.5 zone, yeah. And your surface is right here, and we are looking at the circularity of that, yeah. Of course this is a very exaggerated view, so you're gonna think like, oh no, it's not circular, it's kind of a lot of irregular surfaces right in there, but don't worry about it, it is circular. Yeah, okay. It's just like 0.4 is very minute. Yes, very minute zone right there for you. Okay. All right, then now we'll get into Yes. So this is just showing you that your circular tolerance controls the feature, and your foam tolerance is going to be within the overall size limits. Yeah, the bigger. This is just a legend, but of course, in our printable handout, we make it just a black and white. So just pardon me for this. Yeah, and just but you can see it from here to here. It's your 10 to 11.4 yellow me. That's little one, yeah, little zone right there in between the size tolerance is your 0.4 radial, yeah, tolerance, and this red one is your form, yeah, variation, because you can see this, yeah, how the form is going for that circle within your geometrically controlled limits. All right, so when you look at this, yeah, part, see, now it's outside, yeah, but still inside of the this size limit. Okay, so that's what it say. Well, the part is still within the acceptable limits, yeah, even though it's like come off of there's a 0.4, yeah, because we're like moving this up a little bit, yeah. So this 0.4 zone is still within the size limits, yeah, so it is still acceptable. Now we're gonna bring it down. This is still acceptable because it just this part is now it's smaller than the previous slide part because it's going down here. Your zone of course move with it but still 0.4 anyway. And this 0.4 zone that is including this form variation is still in the size tolerance. Okay. Okay, we're gonna sum them up. So rule 1 cannot be overridden by a circular tolerance. So your actual diameter of your circle got to be within the specified size limit. Okay. Then virtual condition VC is not affected by circularity because modifiers are neither proper nor accepted in your feature control frame. We don't have it. It's off totally. Variation is limited only when the feature departs from your MMC. Okay. By more than the circularity tolerance value. Circularity control establishes independent line trace checks without regard to your datum features. We don't have it. We don't have the datum feature in your control frame. So it's not total surface control. Your circularity tolerance, again, value must be equal to or less than 1/2 the diameter tolerance. Okay? All right. All right, the next one is what we always talked about. Other geometric tolerances is going to indirectly control your circularity. So your other geometric tolerances are your cylindricity, profile, Reynolds, and they're going to influence the circular form of your features. All right, the next one we'll get into the circular control applications. Of course, we're going to check first. Does it apply to the circular feature? Yes, we're going to take a look at your form tolerance. Less than half the diameter tolerance. Meaning like your form tolerance got to be less than half your diameter tolerance. So the little two concentric circles, remember, and you have two pairs of them. That's what we are looking at it. And if that's yes, we're going to look at the modifier in the feature control frame. No, we're going to take a look at our GDT controls, if we have the indirect controls. Yes, we're going to look at our data, the same thing. Now you should get it by now. I've been reading this again and again for you. So datum reference in the feature control frame. No, it is acceptable. No, there is no, it's not applied to your circular feature, they're not acceptable. And if you don't have your form tolerance less than half of your diameter tolerance, unacceptable. Then we look at our modifiers, and modifiers is used in the feature control frame. Yes, that is unacceptable because we don't use it. Then we look at our indirect geometric controls over the circularity, and if that's no, unacceptable. We look at the datum, and if you have the datum, it is unacceptable because circularity is a individual form control. So form controls they don't have the reference datums in the feature control frame at all. All right, so that's your big picture for unacceptable or acceptable. Yeah. Okay. Now we do a little bit of exercise. Yeah, that's problem number 52 in your textbook. So go ahead and take that quiz. Okay, here is the answer. I give it to you. Make sure you do it by yourself and then come back to it. Don't just copy it. Okay, read. This is telling you the same thing, and you should know it by now. Yeah, applying it to the different foam tolerances anyway. All right, now we'll get into cylindricity. All right, so here's a cylindricity. Yeah, there's a little animation that's showing that to you. And of course, so you're outside, we usually use an equipment, which is this one, to measure the cylindricity, your terms and conditions, okay? Your terms and the definitions, yeah? And you can read that through because we're going to cover it in the lectures anyway. All right, so cylindricity, yep, control is usually applied to the external, okay, external feature. So the outer boundary, unlike your circularity. Of course, we always hit the high points of the surface, yeah? Doesn't matter what form control that we're dealing with. So inner boundary is going to radially smaller, yeah, by the amount of the specified tolerance. So the feature got to be at any point of the measurement got to be within the, again, Zeiss limits, yeah? So now you should know that by now. Okay. So when that cylindricity is now going to apply the internal feature, yeah? Your internal boundary is typically established by a gauge contact. Again, we're going to hit the high points of the surface, your internal feature. So the outer boundary is radially larger by the amount of your specific tolerance. Okay. Of course, you can see these outer boundary and things like that. Don't feel bad about it. I'm going to show you in a diagram. Okay, right now you can just read it one time and listen to me one time. It won't go into your head for now. You have to look at it. Yeah, when you need a visual explanation of that. So the feature at any point again got to be again within the Zeiss limits. Yeah. All right. Rule number 1, the same rule. So the default, the automatic control for your cylindricity. We're going to hit, again, your Zeiss feature. Yeah, rule number 1, got to be within the Zeiss limits. Again, upper and lower Zeiss limits, yeah, of your feature establish the tolerance boundaries. So MMC, again, your perfect cylindrical form. Every time you see MMC, you understand you got to put the perfect, yeah, form right in there. If that's cylinder, circular, circular, yes? So perfect cylindrical form is required. So, but the feature Zeiss departs from MMC towards the lower Zeiss limit, then you're going to have to deal with your difference in Zeiss, yeah? Maybe apply to your cylindrical form. That's where your form variations are always come in. Then the greater, yeah, from your MMC. It's just like measuring from the MMC, and you can be able to see how your form variation happen, but they still they still are within the Zeiss limits, okay, to be acceptable. So that's what's saying again the same thing. So form variation can happen because of the straightness of line elements on the surface, roundness at any cross section, a taper at the surface overall. Okay, so let's take a look at what they are with the picture. So here we go. We're gonna have this is your Zeiss limits, yeah, 15.5 to 14.5 shown right here. This time we're dealing with the cylindricity. So you have, look at this, yeah, going, the cylinder length is given to you, 38.2 to 38.8, okay? So since you're dealing with the cylinder, of course, you have a circle and then your depth right there. So that's your rule number 1. Got to stay within that size limits. Then we'll get into by drawing the material. Yeah, so let's put it into there, and you're gonna have 2 concentric circles right there, and that's your tolerance zone. Okay, I just showing you this too. Yeah. So when you subtract 14.5 to 15.5, you got 0.5. Yeah. Now we go into my form. The first form come in here. Yeah. So this is your surface element. Got to lie between the boundaries. Yeah, forming this Zeiss limit right there, and that is going to control the cylindricity. Yeah. So pretty much inside of that, yeah, size limits. Okay, a feature size tolerance zone, again, different. See, the form variation starts right here, but it's still within the size limit, so it's okay. Yeah. So here, since the form varies, yeah, it does allow. So you're gonna just take a look at your MMC, which is this guy right there, away from that. Yeah. So if your socle is closer to the MMC, you will have gotten a perfect, yeah, perfect cylindricity. But right now it's deviated from your MMC, yeah, going towards your LMC. So the form variation, okay, may extend across that range, of course, but as long as it stays within that, yeah, size limits, it's okay. All right, then we go into the next form. See how it's closer to your MMC right there, yeah, but still is accepted. Now we're going to get into exaggerated form. Your upper size limit is right there, okay? So here you can see, look at this, two concentric, yeah, circles right there showing you a breakout section right here. So the upper size limit is your 15.5, yeah, your MMC right here. So as this, okay, form is going to close, getting closer and closer to the MMC, you're getting closer to the perfect form, yeah. So it means that you have a lesser variation, and you have, of course, less tolerance as you go closer to the perfect form right there. All right, the next one, going down to LMC. See, so as you go down, even if there's a form variation is within the size limits right there, you still accept it, yeah. Of course, there are many different kinds of form variation in between the two, yeah, circles right there for your zones, your size limit zone. But again, it can't go outside or inside, yeah, it gotta stay within that. And you can take many different kinds of variation in there. All right, so rule number 1, coordinate dimension, tolerance, we apply rule 1, yeah. Your cylindrical tolerance zone for the cylindrical features is automatically produced, meaning we defaulted it, yeah, meaning like it's got to be within the two limits. And your maximum material condition, yeah, the cylindrical form of the object got to be perfect. Non-stop variation away from your MCC, it can vary in many different ways. As long as they stay within that size limit, you're okay. Your size variation, form error, they are allowed as a departure from your MMC, okay. Your tolerance zone is completely three-dimensional, so your variation can happen, yeah, all along that part. Your cylindrical object can actually be conical or barred or wasted, yeah, depends on your form variation within that size limits, or a variety of all within the limits of the tolerance zone. So the tolerance for your default rule number 1 is going to control your cylindricity, and is limited to 1/2 of your diametrical tolerance, yeah, of your cylinder. Okay, anyway, I don't have to read for that, it's the same thing anyway. Now we get into geometry control for cylindricity. Geometry control again, yeah. We other controls, circular, longitudinal, parallel, yeah. Elements on your surface elements, and we call that the geometric counterparts or geometric controls over cylindricity, yeah. And we don't use a datum, yeah. Cylindricity always apply on your RFS. We don't have a material, yeah, modifiers in your feature control frame. So here, just reiterating everything that we have seen so far, yeah. We don't have a material modifier, material condition modifier in the feature control frame at all for cylindricity. Size envelope is going to impose by your dimension, yeah, limits, meaning your size limits. Rule 1 are never overridden by geometric tolerance for cylindricity. We know that already. So your virtual condition, yeah, of that control feature is not affected. And cylindricity tolerance got to be less than 1/2 the feature diameter tolerance. Okay. All right, so the very first one we are dealing with here is a little symbol, and that's your cylindricity symbol, your tolerance 0.4, okay? And here, of course, your cylinder has a depth, so you have 0.4, yeah? The length of your cylinder. So we can show this way or that way, okay? It's the same thing. Okay, so let's go with cylindricity 0.4, tolerance zone, yeah? So we're gonna put in there, and here is your, of course, your surface of that part. It's just a two coaxial cylinder, meaning like two cylinders, yeah, this and this. You can see it, and coexist meaning like this axis is shared by both cylinders, okay? And of course, it's going to circumscribe, meaning like here is your surface, okay? And these are your high points of that surface, yeah, your cylinder surface, which is this guy. And your true cylinder, okay, is going to encompass that, yeah? Meaning like the closer this all the way to your tolerance zone, then it's better, yeah? Okay. Now we have a size limit 9.5 to 10.5. You have seen this again and again, the same thing. Your tolerance, yeah, is right here. And we're gonna bring all four, yeah. So for a cylinder, so meaning like a two, yeah, coaxial cylinder. So you have 4, 1, 2, 3, 4. If you look at it from the circle point of view, in there. So now your part is going to got to be within the 0.2, okay? So let's take a look at it right here. So when you see this, yes, that's your tolerance. And here, yeah, this is 0.2, the smaller cylinders right here. So that's the 0.2 millimeter, and from here to here is this, yeah, xi is at 10.5 minus 9.5 is going to give you 0.5 millimeters. As long as this tolerance is right in there and your part is right in here, that's okay, yeah. All right, so then we can see it a little bit bigger. So here, this is your tolerance zone, and this is your size limit. Your tolerance zone is 0.2, it's set so here, and here is our form, which is your cylinder, true cylinder, physical cylinder outside. It's now inside of this tolerance zone, see? Now I'm going to go closer to, yeah, this, the lower limit, okay, see that? And of course, the actual feature can vary within the size limit. Now it's going to go up, see? Right? The same thing again here. Your MMC, the closer the MMC, the perfect the form is for your cylinder, of course. Of course, you can't get out of that zone, yeah? And here it seems like out a little bit. But when you look at the form, it's still inside, yeah? So anyways, the other geometric tolerances are always there. Your position profile turnout is going to indirectly control your cylindricity. We say this again and again, yeah, the same thing. So you should know it by now. And review. So we have a cylindricity tolerance, yeah. So we usually show the zones, right? Tolerance zones by using coaxial cylinders to space apart. And that's equal to the tolerance value in your feature control frame as given. Your physical size tolerance again is going to do with your rule number 1, yeah, and it's perfect at your MMC. The control cylinder feature is going to depart from MMC. That sometimes happen and start your variation, okay? Of course, your cylindricity tolerance is going to always limit your maximum, surface variation, meaning like you can go beyond that size limit. So cylindricity tolerance is not going to override your tolerance limits, in rule 1. Rule 1 is called your envelope rule. the mating size envelope is not affected by your cylindricity control. Yeah. So to make sure everything is okay in our design, your cylindricity tolerance got to be less than half your diameter tolerance. Okay. So this is the one in your box, and that's in your size. Yeah, size dimensions given to you. So that the box tolerance got to be less than half of your diameter tolerance. Yeah, you have only two numbers anyway. So cylindricity simultaneously control your circularity, straightness, taper, parallelism. Yeah, all of your cylindrical features. All right. Now we'll get into the application. So we do the same thing and check your cylindrical feature. Yes. Then we're going to check foam tolerance if that's less than half of your diameter. If that's yes, we're going to check our modifier. No, we're going to check our indirect influence of other geometric tolerance over cylindrical tolerance. Then we're going to check our datum. Datum shouldn't be there. Then it's acceptable. Yeah. We check cylindrical feature. If that's unacceptable. Your foam tolerance, we check it. If that is not less than half of your diameter tolerance, is unacceptable. We check modifiers. If you have a modifier, it is unacceptable. Here we check our indirect geometric tolerance, and if you don't have it, unacceptable. We check the datum. If you got the datum, that is not acceptable. Yeah, and here is your two flow charts. How to check your cylindricity. Okay, all right. Then of course we will get into our last part by doing a little exercise. So you're 53, and of course I give you answer right here, and I want you to do this as your homework, and I won't be doing this for you. It's the same thing, the same 5 points right there. Now we'll get into summary. So we have our form 1, okay, and of course we start with our straightness control. Yes, go all the way the same thing. We check the feature, then we check the rule 1, we check the modifier, we check the datums. Yeah. Number 2 is your flatness, circularity, and cylindricity. Yeah. You can apply to a feature, and you cannot apply to a feature of size, and you're going to check the same thing. Control apply to the feature. Rule number 1, control size limit your VC. We check that, and then we check the modifiers, and then we check the data. Okay. So the only thing is right here. Your straightness is the only one where we consider apply to the feature of that. The rest of them apply to the feature. So where your leader line is on the feature. You won't get it by now. You gotta do this again and again, okay, for you to be able to actually get it. And exercise, so please do 54 all the way to 57 in your book. Okay, so that's your work, and I have worked a lot already, over 2 to 3 4 hours. And you're gonna do your 54 to 57, and choose 3 problems out of it. You can also choose what I have already shown to you, so that's up to you. I think 49, we started out from 49 all the way to 57, I think. All right, so foam tolerance. Your problem 54, I give you the answer here, so you can check each one of them, how to go, yes. And here also 55, give you the answer. And here is a 56, I give you the answer. Don't just copy it, okay? I want you to actually do it. And that's why I put it at the end of the lecture, so for you to get that. And here is your answer, Everybody get 100% anyway. These are just your assignments exercise. All right, I'm gonna get get some water and stop right here. When you go to here, even if I give you this example, when we test you or in the final, it's going to be, this number is going to change, okay? So instead of 0.495, plus or minus 0.005, I will give you something else. All right, so make sure when you study this to pay attention. Don't just copy it. I really want you to get it. Yes. I'll give you the correct answer here. If I did wrong or something, just let me know, okay? Sometimes author also was not right. And so make sure you actually work it, yeah, to check. This kind of like a small here. I can make it a little bit bigger for you so you can see it better. I don't know in the handout it's small or not, yeah, but we can actually make it a little bit better. Of course, here, yeah, these are your size limit, and also your feature control frame is attached to each other, yeah, so pay attention to those kind of little things. They all look alike but they're different. Here are the answer, kind of a little bit off, but it's okay, yeah. You know that this is for this blank right here, yeah. And then of course make sure you do each one of them. Don't just copy the answer, because I might, yeah, change this value in the exam. Okay, that's it for today.